Hi everybody, it's Mrs. Peachy, your physics teacher from Wisconsin Connections Academy. As you can see from what's on the background here, today we're going to look at problems on determining net force, and perhaps we'll also start some problems on Newton's first law. So I'd like to work through the sample problem on page 127. So I'm going to go ahead and direct you down to... Alright, so I'm going to go ahead and turn your attention to my notebook, where we will work through some problems on determining net force. And like I said, if there's time remaining, we'll go ahead and work through some problems with Newton's first law as well. Alright, so that should kind of hopefully make that clear for you guys. So the problem on page 127, it says, Derek leaves his physics book on top of a drafting table that is inclined at a 35-degree angle. The free body diagram at the right shows the forces acting on the book. Find the net force acting on the book. Okay, so what it shows us is, it shows us that there's a ramp that is at an angle of 35 degrees with respect to the floor. There's a book sitting on there. We'll just draw it as a dot. And the force of friction on that book is 11 newtons up the ramp. Okay. There's also a normal force on the book, which is from the ramp pushing upwards. And we have the force of gravity on the book of 22 newtons. And as you can see, the force of gravity is perpendicular to the floor, but the normal force is perpendicular to the ramp, and the force of friction is parallel to the ramp. Okay, so it might think that we would want to make our x and y axes using the floor as your x and the force of gravity as your y. But this one actually works a lot better if you tip your coordinates and you use the ramp itself to represent the x-axis. And then you can use the normal force to represent the y. Okay? This makes things a little bit easier. That way we already have two of our forces known in the x and y direction. The idea here is that we want the sum of the x forces, and we want the sum of y forces. And then we can add these together because they are in the same direction, and we can come up with a net force. Now, if we have a net x force and a net y force, then we would just use vector addition to come up with the sum of those two vectors. Okay? This problem, we actually don't end up with that as a problem, though. So, the next step here is to use this arrow and to determine the x and y coordinates of them. So what I want you to notice is that this is a 35-degree angle. This is a 90-degree angle. Okay? So that means this angle here has to be 55 degrees, right? So we want to find this by getting the x coordinate, and then we also need to get the y coordinate. So I'm just going to draw my, my connecting vector here. So our x and our y. Okay? And we know this angle is 55 degrees. So what I can do is opposite over hypotenuse, so the sine of 55 equals y over 22 and adjacent over hypotenuse, the cosine of 55 equals x over 22. Then we get 22 sine 55 equals y. 22 cosine 55 equals x. When I do the math to solve for that, I end up with y equals 18 newtons and x equals 13 newtons. And I'm rounding to the nearest whole number there. Now remember, because we are now kind of in the opposite direction, we have to determine, positives and negatives. And I'm going to say that positive, positive, negative, negative. I'm going to use the coordinate directions like you would expect. So our total y, we have a positive 18 newtons. And we have one that's pointing down, so that's a negative 18 newtons. Those are our y coordinates. Our x, I have a negative 11. And I have a positive 13. So when I sum these, 18 and 18 give us a sum of 0 newtons in the y direction. And negative 2 newtons in the x direction. So just remember that the negative here does not determine value, it tells us direction. So we already determined that, that's positive 2, my bad. We already determined that positive meant down the ramp. So rather than writing positive 2 newtons, I would put 2 newtons down the ramp. Okay. Another problem I'm going to work through then is a problem on page 132. So if you turn to page 132, practice set C, there are a number of different problems here, but I want to work through problem number 5 because that was the most difficult problem. So this is using Newton's second law. Remember, Newton's second law says that force is equal to mass times acceleration. Okay, so that's a mathematical definition of the law. So this says a 2-kilogram otter starts from rest at the top of a muddy incline that is 85 centimeters long and slides down to the bottom in 5 seconds. What net force acts on the otter along the incline? So we have to kind of remember some of our kinematic equations for this because we need to know what the acceleration is on the incline. So you can't use gravity because gravity acts only in the vertical. So we need to find out the acceleration down the ramp, right? So A. We know the mass of this otter guy. Such an ugly otter. Is, what is he, 2 kilograms? And we need to know the net force acting on the otter. Okay. So we need to find out what the net force is down the ramp. What we do know is we know the length of the ramp is 0.85 centimeters, and we know the time it takes to get to the bottom of the ramp of 0.5 seconds. Sorry, 0.85 meters. It was 85 centimeters and 5 seconds. One of our kinematic equations tells us that x is equal to 1/2 a t squared. So this equation works very well in order to get us the value a. So 0.85 meters equals 1/2 a, and then I'm sorry, 0.5 seconds. Okay, so I square my 0.5 seconds. That gives me 0.25. I'm going to divide both sides by 0.25. And then I also multiply both sides times 2. That gets rid of this 1/2. Okay? So doing all of that gives me that acceleration is 6.8 meters per second squared. So it's easy to forget the kinematics because they were last chapter, but they help in solving any equations, any problems using straight line motion, right? So we just have to use one of those equations. So now we have acceleration and we have mass. So that allows us to do mass times acceleration. To get force, which rounded gives us a force of 14 kilograms meters per second squared, which is better known as a Newton. 14 newtons. Down the ramp. That is. So when we're looking at problems involving ramps, you got to remember that the motion indicates the direction of net force. That's what was going to be revealed to you when you started using your free body diagrams. The direction of net force is the direction of motion. Okay? If the object is stationary, then the net force is 0. So keep that in mind because that's going to help you determine the direction of the force. Magnitude, you have to use the equations to figure out. All right, so those are some practice problems from today's lesson on determining net force and Newton's second law. If you have additional questions, feel free to call me at extension 2204, or you can send me a webmail message. Have a great day.